So one of the question, one of the participants, if you recollect, asked you is that you are a great believer in the power of ML as well as causal inference, and kind of bring those two together. You also had an interesting meme. We will of course share that meme. I'm also a big Dragon Ball Z fan, and the fusion of that is causal AI that you have put forth excellently. Can you talk more about it? Like, I know it's a very new field. Uh, what can people expect from it? What is the drawing power, so as to speak, of causal AI?
Yeah, fantastic question. I love to speak about this. Indeed, it's a really growing field, but still, which is very well rigorously tested and come from scientific research, mainly from, let's say, Susan Atte from Stanford, from Viktor Chernozhukov, Guido Imbens, so Nobel laureates in economics from MIT. So again, you really have this very solid models and a lot of work more recently by Professor Martin Huber, also in Switzerland. So long story short, basically, we have talked early that you have traditional AI and predictive inference. And on the other, you have another toolbox called causal inference. You want to answer causal things. There are different toolboxes to answer different questions, and you should not mix them for the reason we highlighted. Predictive inference relies on correlation. Then, it led to the second step. Basically, we discussed earlier also this very hot topic that actually you should use them together in the following sense. Traditional AI, predictive AI, requires the use of causal AI to measure the business impact. So you deploy a recommendation algorithm, you want to use causal inference to know the business impact of this recommendation algorithm. Same with a chatbot, same with this AI model. So you need to use them both. And in particular, predictive inference, predictive AI, needs causal inference. Now we arrive in this final step, unification, the one you just mentioned, causal AI. Causal AI is kind of the opposite relationship, is when you use predictive inference to help with causal inference. When you use predictive AI to help with causal inference. And you can do this at several steps, several stages that I will highlight mainly three main applications. So that's one thing, something that I really want to stress, because many people see the term causal machine learning, causal AI, and they think now it adds to the confusion. Basically, they think that now they can use AI for just traditional predictive AI model to do causality. It's not the case. It's still not the case. Causal AI is still you start with causal inference. And then basically you sprinkle a little bit of predictive inference, predictive AI to help you. So let's highlight three use cases. The first is about A/B testing and how to augment A/B testing. So basically in A/B testing, traditionally what we have been doing to measure the effect of some campaigns and compare options is to compute the difference between, in the simplest case, between two options. And you see higher conversion is in option A compared to option B. Good. Many people will just want to roll out and implement option A. The thing is, when you do this, historically, in causal inference, we focused on average treatment effect, AT. We want to measure the average effect of the treatment. So on average, the conversion was higher with option A. Good. On average, it's a good metric. It's a useful metric. But the average, of course, has some limitations. It hides the variability, the heterogeneity. And essentially, what we can do with causal AI is uncover the heterogeneous treatment effect in a very efficient way. It's basically you roll out your A/B testing, and then in a second step, so you roll out A/B testing with traditional causal inference, and in the second step, you use a predictive AI algorithm that is made for this, for example, causal forest, which will uncover, it will try to discover subgroups who answered differently to the treatment. It will try to understand what are the subgroups who really liked option A, who really liked option B, and so on and so forth. So it allows you to see that maybe on average it works better for option A was preferred, but you have a subgroup that actually really preferred option B. And then this helps to do some personalization, to answer the fact that we know that the world is complex, and hence to be way more efficient with our recommendation because it adapts to the different target audience. So that's one thing. It's one application, heterogeneous treatment effect with causal forest. The second one is the one I taught during our joint class, during your class where you invited me, which is double machine learning. So it starts like this. If you've done a bit of causal inference, you know that the foundation of causal inference is basically you want to control for the confounders. So you want to measure the effect of X and Y, and you have a bunch of confounders, meaning things that affect X and Y, and you want to capture their effects. Backdoor path, you have different terminology. Block the backdoor path. But one thing that many people, and I'm obsessed about functional form because many people forget about this, is that many people will say, well, you know what, I will just include these variables as controls, as control variable in a multiple linear regression. When they do this, usually they don't think twice. They just include them as linear controls without pausing for a second thinking. Maybe this is a strong assumption. Maybe they have non-linear relationships. Maybe they have interaction effects. Maybe the functional form of what we call the nuisance function, the function of the controls, is very complex. And basically, machine learning is really good as to find good functional form. So that's the essence, basically the starting point of double machine learning is we are going to give to a machine learning algorithm the task to find the best functional form for the nuisance function, for the function of the controls. That's basically the essence. You know that it's a bit more complex and involve a two-step
Yeah.
methodology. Actually, more than two steps because you have three different computations.